Your Libby algorithm knows a lot about you, and so does your local library. Maybe you're all about calming self-help guides, or you're more the romantasy type because dragons and kissing are a killer combo. Or maybe you're a bit of both, like Dostoevsky. But that might look pretty different from what your best friend's reading. And even if you aren't nosy about those differences, you better believe your Libby algorithm is. Now, fairy romances aren't numbers, but we can still use them to make comparisons and suss out important patterns because stats can deal with more than just numbers. Hi, I'm Sabrina Cruz, and this is Study Hall, Real-World Statistics. Usually, statistical tests look at the numbers to compare things and understand relationships, like book sales. But sometimes we don't have numbers. In that case, we can also compare categories. Now, when I say categories, I mean lots of things, like neighborhood libraries, types of flowers, or all of the beige ingredients that go into a tuna casserole. Now, those are all categorical data that are divided up into groups instead of being represented by numbers. And when we get down to the level of individual data points for those things, we don't have pieces of information like 1 or 2. We have mayonnaise and celery. Because these data look different, the tests we've learned about so far won't work on them. But there's no need to panic. We can still work with these data. Now, my buddy Jose, who is definitely real and for sure exists, helps manage the stock across 7 different libraries in the town of Knockemstiff, shuffling books around depending on demand and emerging trends. The neighborhoods of each library are pretty different, and they have an evolving mix of library users, which means different patterns in what kinds of books they borrow and how often. The city council contacts Jose, telling him that they're caught up in a tangle over the library system's budget. Jose tries to remember the last time the city council was not caught up in a tangle over budgets, but he decides not to bring it up. They want to know if they can make a single decision on how money is split across the libraries for the next 5 years, or whether it's the kind of thing that they ought to return to and reallocate every year. Now, the funding gets split depending on how busy each library gets. If that looks the same year on year, they can cross it off their list for the next 5 years without having to worry about it. But if it changes, they'll have to revisit the budget each year to make sure staff and resources go where they're most needed. Otherwise, they might face the unthinkable: library closures. Understandably, this is Jose's worst nightmare, and he is not going to let it happen. So our book-loving hero sets out to investigate whether borrowing patterns changed across libraries between years. The thing is, Jose knows how busy each library gets could change. Like in cool and trendy Median Heights, the regulars love Sally Rooney and George Eliot, unless there's a new Brandon Taylor out and more people show up. Then there's the bustling office blocks of Skewness Square, where they're really only into new Malcolm Gladwell releases and won't read anything else. There's also the quiet leafy streets of Markov Meadow. Last year, those dudes were all about Elena Ferrante, but this year they're only coming in if Rebecca Yarros is in stock. Fickle. Jose's categorical variables are the 7 individual libraries, both this year and last year, and he wants to see how many times books were borrowed from each location during both periods. He knows that he'll need to compare the libraries this year to last year, and that he'll be doing some hypothesis testing. Jose's alternative hypothesis is that this year's distribution across libraries is different from last year, because, let's be real, he knows that the patrons of spot like Markov Meadow love to change their borrowing habits based on what's the hot new book, even if that leaves Ferrante behind. Meanwhile, if there's no difference since last year, a frequency distribution of books borrowed across libraries for this year would look very similar. That's his null hypothesis. It basically says he has an idea about what last year's frequency distribution of book borrowing looks like, and that this year's frequency distribution will look like that too. The distribution we want to compare our sample data set to is called the theoretical distribution. It's a kind of theory about the world that we're putting to the test, but in order to do that, we need to compute expected values. Those are the values you would expect to get if the null hypothesis were true. The sum of all of our expected values should be equal to the sum of our observed values, or sample size. For Jose, as he figures out this year's borrowing patterns, his theoretical distribution is the borrowing patterns from last year. He relies on that theoretical distribution because his null hypothesis is that there will be no change, and Jose uses that theoretical distribution to determine the expected values. He compares the expected values with his observed values, or sample data set, to determine if there has been a change in the borrowing patterns at the libraries. But Jose knows that just because things looked one way last year doesn't mean that they'll look that way this year. This year's actual frequency distribution might be different than the theoretical one, which is why we have to run the test. Maybe the rates at Skewness Square Library have gone up, or dropped much lower because Malcolm Gladwell has nothing new coming out. The same might be true for any of the other libraries. It might seem impossible to compare 7 different libraries across 2 years at once, but let's actually think about what we're interested in. To test how different the real data look from our theoretical distribution, Jose needs a way of measuring how different, on average, those borrowing rates really are. That's where the chi-square test comes in. It's a measure of exactly how different the theoretical and the true frequency distributions are based on how much the heights of the bars differ, which is exactly what my poor book-loving buddy Jose needs right now to keep the library budget on track. And the idea with chi-square test is sort of like the way we calculate standard deviation. We take the difference between what we expected to happen if the null hypothesis is true and what we actually observed happen for every category in our distribution and square it. Then we divide it all by the expected number so that the measure of distance is comparable between each bar. Then we just add the same thing up for every category. That means Jose's chi-square would involve subtracting the observed values for this year's borrowing from the expected values from the theoretical distribution, which we've decided is last year's borrowing rates, then squaring that number and dividing it by last year's borrowing rates. He would do this individually for each library, then add all of these values together. This idea of squaring a difference so that we always get a positive number, just like in a standard deviation, is why this statistic is called the chi-square. Working with positive numbers is important because otherwise differences can cancel each other out, which makes it seem like less change than it really did. And if you want to dive a little bit more into the math, we've left some resources for you in the description. But here's the upshot of all this. The chi-square is exactly the measure we need to tell how much one frequency distribution looks like another, which is great news for Jose and his book budget mission. Remember, his null hypothesis is that this year's data will look similar to last year's data, and his alternative hypothesis is that there is a significant difference between the two. But to be clear, Jose's not saying that the values in each category will be generally higher or lower, just that at least one category will be different in some way. Another way of thinking about this is that Jose's testing how well the data fit a particular set of predictions made by his theoretical distribution. That's why the chi-square test and other tests like it are often called goodness of fit tests. Depending on the number of categories being considered, we subtract one from that number to get the degrees of freedom, which are like the flexibility that the data have while still following certain constraints. For practical purposes, all you need to know is that in a chi-square test like this, it's one less than the number of categories. Jose is looking at 7 libraries, so the degrees of freedom are 7 minus 1, or 6. That number defines a special kind of probability distribution called a chi-square distribution. The math here gets pretty involved, but each probability distribution for a certain degree of freedom basically spells out how likely it is that you would get a certain chi-square value if the null hypothesis is true. For Jose, that represents the probability distribution that his chi-square number would look a particular way, even if the true underlying pattern in this year's distribution resembled last year's patterns. Just like other test statistics, the goal of the number we calculate, the chi-square value, is to see how far off the observed data are from the null hypothesis. And like other statistical tests you might have done, the area in the right-hand tail of the chi-square distribution is the critical region of our test. This is the area where the data we're seeing are so different from what the null hypothesis says that it's unlikely to come about if the null hypothesis is true. And as with most stats tests, we have our p-value, or the number describing how likely it is that our data occurred under the null hypothesis. So, looking at Jose's chi-square distribution with 6 degrees of freedom, this region on the end would be larger or smaller depending on the significance level threshold we set for our test. Then, just like every other statistical test, if Jose's chi-square falls outside the critical region, he'd fail to reject the null hypothesis. Basically, it would mean that the frequency distribution of this year's borrowing looks too similar to previous year's distribution to say that there's any meaningful difference. But if Jose's chi-square falls into the critical region, that would suggest that this year's distribution is significantly different than last year's. He'd reject the null hypothesis and conclude that those borrowing rates were different. Now, that's a good outline for how to test a hypothesis, but practically speaking, it's pretty hard without a computer. Thankfully, performing a chi-square test is pretty easy using spreadsheets and other programs. Jose chooses Google Sheets to solve his problem, but you could use most other programs too. Jose has the names of each library, which are his categories, in one column, and 2 columns for the book borrowing data for both last year and this year. He sets a p-value threshold of 1% and in a new cell puts in an equal sign, then CHISQ for chi-square, followed by a dot and then test, all in capitals, and then an open parenthesis. In the brackets, he puts in the range of cells for the observed data, a comma, then the range of cells for the expected data, and then a closing parenthesis. All of this basically says, hey, run a chi-square test on these two columns of data, check whether the distributions of data look similar to each other, and calculate the p-value for this test. It's nice when you're starting to get fluent in computer. Anyways, for Jose, the result is a p-value which comes out significantly smaller than 1%. That tells Jose that the trends in borrowing across the libraries really does seem to have shifted since the previous year. And maybe that means it could change again next year. So he tells the council they should probably revisit the budget again in 12 months if they want to make good use of their money. And that'll mean money going to the right places, even if it means the city council is once again in shambles. Whether you're trying to preserve your local book sanctuary or doing something like comparing distributions of students across different schools, goodness of fit tests are incredibly handy. They help show how well a set of predictions matches up to real-world data, or whether two distributions really are distinct from one another. That's super important. The theoretical distributions researchers work with are often precise and quantifiable predictions about the world. Whether it's the distribution of particles in the Large Hadron Collider, the hospitals most likely to be affected in an outbreak, or just the books you think that someone will check out from their library right before their summer vacation. Tamara Pierce? Anyone? Anyone? If you're enjoying this series and are interested in taking the full Study Hall Real-World Statistics course and earning college credit from ASU, check out GoStudyHall.com or click on the button to learn more. And if you want to help us out, give this video a like, smash that subscribe button, and comment your favorite book genre. Thanks for watching, and see you next time.